British humor. It is pretty good. So, impedance is lecture 3.2. I stayed up late last night preparing these lectures, and like, I had a lot of fun doing it. This is fun stuff. I got to use emojis. I don't think I used one in this lecture. I was definitely effing up when I did this. I should have. I even found, like, there are some really cool ones. I can, like, color them and stuff. Yeah. We'll get there. Okay. So, impedance. With complex representations of voltage and current, we can introduce the concept of impedance, which I've been talking about really since day one. I was like, resistance, but impedance, guys. Okay, so here we are. We're finally there. Impedance, Z, is the symbol we use for impedance, is the complex ratio of voltage to current of a circuit element. So the impedance of a circuit element is the ratio of the voltage across it to the current through it. Now, this looks a lot like another definition. What was this? What does this look a lot like?
Ohm's law.
Yeah, exactly. It's the definition of resistance, which is Ohm's law, right? The resistance is the voltage drop across the resistor divided by the current through it. So that is very much in the background of our minds when we see this. So the real part of the impedance is called the resistance. And the imaginary part is called the reactance. As with complex voltage and current, we can represent the impedance as a phasor because it's a complex number, so it has a magnitude and a phase, so we could represent it as a phasor. So note that this definition of impedance is a generalization of Ohm's law. In fact, we call the following expression generalized Ohm's law. So instead of V equals IR, V equals IZ. What's cool about it is that the impedance of a resistor is still a thing. It's not just the resistance. But now we can write the impedance for the inductors and the capacitors as well. So this equation, this generalized Ohm's law, is going to apply to resistors, capacitors, and inductors, not just to resistors, like good old-fashioned Ohm's law with just resistance. Okay, so the impedance of each of the three passive circuit elements we've considered thus far listed below, wherever it appears, omega is the angular frequency of the element's voltage and current. So if you're plugged into the wall, that AC source is at 60 hertz. So you have to multiply that by 2 pi. So 2 pi times 60 would be the omega for some, say, a capacitor that you hook up to the wall. Okay? All right, so for a resistor with resistance R, the impedance is all real. So ZR is equal to R e to the j 0 in phasor form, which e to the 0 is what?
1.
So we just left with R. So in rectangular form, it's just R, and there's no imaginary part. In phasor form, it's R e to the j theta. Okay. Capacitor. For a capacitor with capacitance C, the impedance is all imaginary. So ZC equals, it's 1 over omega C times e to the minus j pi over 2. So the magnitude is 1 over omega C. The phase is negative pi over 2, which is negative 90 degrees, right? So if we were to represent this in a rectangular form, there's 0 real part, right? The imaginary part is negative j times 1 over omega c. Sometimes this is written but I think it's not as preferable in my opinion. 1 over j omega c, because you can move the j to the bottom by multiplying the expression by j over j. J times j is -1, so the denominator gets the j, and you get to get rid of the sign, which makes it a little neater to write that way. But when you want to combine this with other things, you want the j in the numerator because you want it to be whattionalized, rationalized. Did you guys do this with complex numbers back in algebra or something? They were like, hey, here's a complex number, but it's like in a fraction. They're like, rationalize the fraction. And you're like, when the hell am I going to use this? Now is the answer. Right now. Back when you're sitting at that desk and you were thinking, this is not useful, you didn't know you were going to be here one day. It's forgivable, though, because, I mean, you were young.
It's actually
I mean, maybe you weren't young. I don't know. It's hard to say.
It's not useful.
So, inductor. So, yeah, we've got this representation for the capacitor. Now let's also look at the impedance of the inductor. For an inductor with inductance L, the impedance is all imaginary. So I'm going to write it on this page at the top. ZL equals, it is just omega L e to the j pi over 2. Which is to say magnitude omega L, phase pi over 2, or 90 degrees. And this is, if we were to write it in rectangular form, we'd have no real part again, but this time it is all imaginary and it is of length omega L. So all three of these can be easily drawn in the complex plane, right? All three of these impedances. So let's go ahead and do that. The resistor, the resistance is the real part, right? So resistance R is just all in the real direction, and magnitude R. The reactance dimension is this imaginary part, right? And so for the inductor, it's j omega L, so this has length omega L. It's in the positive imaginary direction. And ZC is negative 1 over omega C, so this is in the negative j direction. Now, we're about to learn how to combine these things in like parallel and in series. And so what happens when you start adding these things, it's just like adding vectors. You're going to end up with ones that are not all along one of the axes, right? You're going to end up with something with a real and an imaginary part. In which case, you just have some impedance that has some phase and some magnitude. Okay? So that's what we're going to get to in just a sec. All right. So, combining the impedance of multiple elements. As with resistance, the impedance of multiple elements may be combined to find an effective impedance. So K elements with impedance is Zj. Well, see, I used the J there as an index. Probably should have gone with like a lowercase k, because I used a big K too, but that's a little hard. I don't know. Too few letters. All right. Connected in series have equivalent impedance ZE given by this expression, where you just add them. Add the impedances. It's just like resistance, right? And it better be, because remember, resistance is a subset of impedance, so we wouldn't expect it to be a different rule in the general case. So if you have impedances in series, you add them. If you have impedances in parallel and you want to combine them to an effective impedance, you combine them with this expression 1 over the sum of the inverses of the impedances. In the special case of two elements with impedances Z1 and Z2, we can write that the equivalent impedance is, of course, it's 1 over Z1 plus 1 over Z2, but we could simplify that into our familiar yet fresh expression Z1 Z2 over Z1 plus Z2. it's just so much better with Z's. Wouldn't you agree?
Agreed.
I mean, it was fine with R's, but I feel like they're better with Z's. So this is same stuff, right? It's the same. This is familiar. It's just from resistances, combining them in series and parallel. Now we're doing it with impedances in series and parallel. Oh, look. We get an opportunity to try out some of this information. So, given the circuit shown with a voltage source A e to the j phi, sinusoidal voltage source is what that means. It has amplitude A, phase phi. Notice that it kind of matters which sort of implied trig function you're coming from, right? Is it cosine? Is it sine? It does matter. But, so if it's given in the problem, you got to go with whatever is given, cosine or sine. If it's not given in this class, we'll just have the convention that it's just cosine, unless otherwise stated. But if the problem starts out and this is a sine, then your phasors can represent sine phasors. You can have sine phasors or cosine phasors. They're just different by pi over 2, right? So you have to make a decision. And in this course, we're just going to say it's cosine. So if you were to, at the end, convert this to a trig form, you would convert it to a trig form with a cosine. Because it wasn't stated in the problem where it came from. So, and that's why I used cosine throughout this lecture. So that if you go back here confused, you're going to accidentally get it correct, even if you don't understand it. Because I used cosine throughout the lecture. I know, I'm thinking about you guys. Okay, so combining these, so it's given the circuit with A e to j phi. What is the total impedance at the source? So what does this circuit look like to the source is what I'm asking in terms of impedance. If these were resistors, we would be like, oh, let's combine these and see what the resistance is that the voltage source feels. Now we can't do that because they're not all resistors, but we can do it with impedances, right? So we did a problem quite similar to this when we had resistances. So let's see if we can do the same thing. I think it's just a one-line problem, right? ZE is equal to the impedance of the resistance in series with the impedances of these two in parallel, right? So plus ZL, ZC over ZL plus ZC. And in a certain sense, we're done, right? We're done. But we want to learn how to simplify this expression. We know ZR and ZL and ZC all have these definitions of their impedances that we wrote down, but we want to see how they start to combine and what this looks like. So we did the hard part. Now let's plug in the known impedances. So the impedance of the resistor is just R, right? Plus, now I'm going to write this because the numerator by itself and the denominator, because they're kind of big. So ZL is in phasor form, let's use, it is L omega e to the j phi, or pi over 2, I should say, pi over 2. And it's multiplied by, what is the impedance of the capacitor?
1 over j omega c.
Yeah, but we're going to use phasor form, so e to the j, or e to the minus j pi over 2. So that's the numerator, right? The denominator, we could plug in the same impedances, but we're actually going to do something that requires experience, and I'm now going to pass on to you. That is that if you're going to multiply phasors together or divide phasors, phasor form is the way to go. Okay, complex voltages and currents and impedances, phasor form is the way to go. If you're going to add and subtract them, rectangular, aka real and imaginary form is the way to go. And in the denominator, we're going to be adding them. So let's write them in rectangular form. So ZL is just JL omega. And for the capacitor, it was, well, minus, right? It's negative J 1 over omega C.
If you changed and used the 1 over J omega C, would it still get the same answer for the capacitor portion? Yeah.
Yeah, I mean, yes, but you're just going to have to do more algebraic steps. And so that's what, like, I'm saying, yeah, technically you could plug in the phasor form in the denominator too if you want it. But you're going to find that then you got to add them, and it's not quite clear how to add them unless you break it down into the real and imaginary components anyway. So you're already going to go there, so we just did it immediately. So that's why we looked ahead and we saw that. So we're going to multiply these. The omegas cancel, right? Yeah, so we have L over C times e to the j pi over 2 times e to the minus j pi over 2. And so when you multiply exponentials, you add their exponents, right? So it's e to the 0, which is just 1. Well, that worked out nicely. The denominator, you can factor the j out, and then you can combine these two. You can add them by finding a common denominator, right? Which is omega c. So we're going to have LC omega squared minus 1 divided by omega c, right? Whew. Getting there. Wait. There was another parenthesis there. Okay. There, that we got it right. Because this is, yeah, j times all of this. Because we factored out the j. Okay, so now we're getting very close. We can even, so the L over C up here, we're going to multiply the numerator and denominator by omega c. So the c's cancel, and we end up with L omega in the numerator. And the denominator, we have left j L C omega squared minus 1. Right? All right. Now, we want to combine this resistance with this term over here. And now, if we want to do that, we can multiply by j over j and get minus j L omega LC omega squared minus 1. So this is actually totally simplified in rectangular form. If we wanted to write it in phasor form, we're going to have some magnitude, which we're going to have to compute, and e to the j some phase, which we're going to have to compute. So we're going to compute them using, first off, to find the magnitude. It's the good old Pythagorean theorem. So we need the square root of the real part squared, which is r squared, plus the imaginary part squared. The imaginary part is negative L omega divided by LC omega squared minus 1. All that is squared. And that's all under the square root. So notice, so key point here is that we took the imaginary part. We did not take the j with the imaginary part. If we did, it would be incorrect. Because when you take j squared, you get a -1, and then it changes the sign here. And we're off to the wrong races. We want to go to the correct race. The phase, we're going to use a little trigonometry here. So we use Pythagorean theorem to compute the magnitude. The phase, we're going to use arctangent of the imaginary part over the real. Opposite over adjacent. So it's the arctangent of the following big fraction. So it's the imaginary over the real. The imaginary part is this, right? So it's negative L omega divided by LC omega squared minus 1 divided by the real part, which is R. So we're done. I mean, we could simplify that last. We could put the R through the denominator. That's about it. So the main thing to keep in mind, though, is that once we wrote this down, we were done, right? All we needed to do was simplify. Okay. All right.
I'll watch this lecture.
I'll see you on Wednesday.